We now discuss the solution of a problem from the section Analysis. The problem is based on the uniform convergence of the series of functions of two variables. This question has appeared in CSIR National Eligibility Test held on 26th November 2020, and it is from the section B and it carries 3 marks. The problem is, let f be a function from r squared to r, which is defined by f of x comma y is equal to 2xy by x square plus y square when x comma y not equal to 0 comma 0 and f of x comma y is equal to 0 when x comma y is equal to 0 comma 0. Define g of x comma y as sigma n is equal to 1 to infinity f of x minus n comma y minus n by 2 power n. This is the series, and the series is equal to g of xy. Which of the following are true? Options. First option is the function h of y is equal to g of c comma y is continuous on R for all c. Option 2. G is continuous from R square into R. Option 3. G is not a well-defined function. Option 4. G is continuous on R square minus the set of all ordered pairs k comma k belongs to n. Let's now discuss the solution of the problem. First, let's take the statement that is given in option 3. G is not a well-defined function. We have the function r square to r defined by like this. And g of xy is defined as sigma n is equal to 1 to infinity f of, in the place of x minus n, comma, in the place of y minus n, whole by 2 power n. And we have to decide whether this function g is well defined or not. Now, we first show that f of x comma y is well defined. If f of x comma y is well defined, then sigma of f of x minus n comma y minus n is well defined, by 2 power n is well defined, this summation is well defined, thereby g of xy is well defined. Now, if x1 comma y1 ordered pair is equal to the ordered pair x2 comma y2 is equal to 0 comma 0, then obviously f of x1 y1, that is f of x1 y1 at the origin is 0, f of x2 y2 at the origin is 0. They are equal. Let x1 comma y1 is equal to x2 comma y2, where x1 comma y1 is not the origin and x2 comma y2 is not the origin. Then f of x1 y1 is equal to, by definition, 2x1 y1 by x1 square plus y1 square. But we have x1 y1 is equal to x2 y2. So x1 is equal to x2, y1 is equal to y2 is substitute, and that will be equal to 2 times x2 y2 by x2 square plus y2 square, since x1 comma y1 is equal to x2 comma y2, and this is equal to f of x2. Thus we have proved f of x1 y1 is equal to f of x2 y2, and this shows that f of x comma y is a well-defined function. So therefore g of xy is equal to that sigma n is equal to 1 to infinity f of x minus n comma y minus n by 2 power n is a well-defined function. So our option 3 is not true. Now we take the options 4 and 2. Option 4 says G is continuous on R square minus the set of all ordered pairs k comma k belongs to n. And option 2 says G is continuous from R square into R. So one of them may be true or both of them may be true. So we have to now discuss now. We have the function and we have g of x comma y defined as sigma n is equal to 1 to infinity f of x minus n comma y minus n by 2 power n, and this f of x minus n comma y minus n by 2 power n, call it as gn x comma y. So that will be this sigma is equal to sigma n is equal to 1 to infinity gn xy, where gn of x comma y is equal to f of x comma x minus n comma y minus n by 2 power n, and that is equal to, write down the definition of f of x comma y in terms of x minus n and y minus n, and we get 1 by 2 power n is equal to 2 times x minus n into y minus n by x minus n whole square plus y minus n whole square. That is the gn of x comma y. First, note that f of x comma y is continuous everywhere on R square except at the origin. So the disturbing factor for the continuity is the denominator, that is x square plus y square. So now therefore each function gnxy, gn of x comma y will be what? That will be equal to 1 by 2 power n into 2 into x minus n into y minus n by x minus n whole square plus y minus n whole square. So this will be continuous provided it is continuous at the denominator. So in the denominator you have x comma y is equal to n comma n. There the continuity is lost. Therefore gn x comma y, n belongs to n, is continuous everywhere in R square except at those points n comma n, n belongs to n. That is, each function gn of x comma y, n belongs to n, is continuous on the set E is equal to R square minus the set of all k comma k, the ordered pair k belongs to n. So thus we have decided this in this series each term gn of x comma y is continuous on E, where E is R square minus the ordered pair k comma k belongs to n. So we are now deciding the options 4 and 2. So we have gn of x comma y, which we have seen, that is equal to this, and each is a continuous function on R square minus the set of all k comma k belongs to n, which we have called it as E. Now take the modulus gn of x comma y is equal to modulus of this is equal to, you take out 1 by 2 power n modulus of the remainder, and you notice that the modulus of this is less than or equal to 1, and thereby you will get it is less than or equal to 1 by 2 power n, and call it as mn. And why this is less than or equal to 1 by 2 power n? Because modulus of 2 into x minus n into y minus n by x minus n whole square plus y minus n whole square is less than or equal to 1 for all x comma y belongs to E. E is the set of all R square minus the set of all ordered pairs k comma k belongs to n. It is less than or equal to 1 by 2 power n is equal to mn. And further, sigma mn is equal to 1 by 2 power n is convergent, and it is a geometric series, and whose common ratio is 1 by 2 less than 1, and it is convergent. And now we apply the mn test for series of functions. Now by mn test, sigma n is equal to 1 to infinity gn x comma y is uniformly convergent on E. Now the sigma gn x comma y is uniformly convergent on E, and each term of the series is continuous on E. Therefore, there is a theorem called the continuity theorem that says it's a sum function. It's a sum function. Sigma n is equal to 1 to infinity gn x y. The sum function is g of x comma y is also continuous on E. That is called the sum function. Each function gn x comma y n belongs to n is continuous on E. That is each term of that series. And this series sigma n is equal to 1 to infinity gn x y is uniformly continuous on E. Then it's a sum function. The sum function is g of x comma y is continuous on E, and this theorem is called the continuity theorem. Thus, g of x comma y is continuous on E is equal to r square minus the set of all ordered pairs k comma k belongs to n. So therefore, the option 4 is true, and obviously the option 2 is not true. We continue in the next slide. Now, we have already discussed the first three options. Option 2, 3 and 4 we have already discussed. The option 1 is left, and the option 1, the statement says the function h of y is equal to g of c comma y is continuous on R for all c. So in the place of x we are taking a c, a constant, and thereby it is becoming a function of y. And we want to show that this function h of y is continuous on R. And we have g of x comma y is the sigma n is equal to 1 to infinity f of x minus n comma y minus n by 2 power n. H of y will be g of c comma y. Wherever there is x, you write c. And let us call this as the gn of y. So sigma n is equal to 1 to infinity of gn of y. Gn of y is this. So where gn of y is f of c minus n comma y minus n by 2 power n, that is equal to 1 by 2 power n into 2 into c minus n into y minus n by c minus n whole square plus y minus n whole square. Now we deal with two cases, and we want to show that it is continuous on R for all c. And we consider two cases when c does not belong to n, that is when c is a real number but not a natural number, and the other case is when c is a natural number. So let us take the case 1. Suppose that c does not belong to n, that is c is a real number but not a natural number. Then when c is not a natural number, c minus n for any n belongs to capital N is not 0. Is not 0, and thereby c minus n whole square plus y minus n whole square is not equal to 0 for all n belongs to n and for all y belongs to R. So that this is the denominator. The denominator is not disturbing the continuity. Therefore, the whole function will be continuous, and thereby gny will be continuous. Therefore, gny n belongs to n is continuous for all y, and that is gny n belongs to n is continuous on R. Now, mod of gny is equal to mod of this, and that is equal to 1 by 2 power n to mod of this, and the mod of this is less than or equal to 1, and that is less than or equal to 1 by 2 power n, that is mn, and sigma mn, that is equal to sigma 1 by 2 power n is convergent. By Weierstrass M test, sigma n is equal to 1 to infinity gny is uniformly convergent on R. So this series is uniformly convergent, and each term gny is continuous on R. By continuity theorem, its sum function h of y, that is equal to g of cy, is also continuous on R. By continuity theorem, its sum function h of y is equal to g of c comma y is continuous on R when c is not a natural number. So the first case, in the first case, the option 1 is true. And in this, what we have considered, what has happened is, instead of this series of two functions of two variables, it has now become series of functions of one variable, and the same method is applied. And similarly, in the second case, so we have g of x comma y, and we have h of y, that is equal to g of c comma y. And now we consider case 2. Suppose c belongs to n, and let c is equal to m, a natural number, where m is arbitrarily chosen element of n. Agreed. Then hy is equal to, wherever there is c, you write m, g of m comma y, and that is sigma n is equal to 1 to infinity in terms of f. And that is equal to sigma n is equal to 1 to infinity 1 by 2 power n into 2 into m minus n into y minus n by y minus n, m minus n whole square plus y minus n whole square is equal to sigma n is equal to 1 to infinity g and y. So you know what is g and y? G and y is this 2 into m minus n into y minus n by m minus n whole square plus y minus n whole square. Suppose you take n is equal to m, n is equal to m, then m minus m will be 0. So that means g m y, that is the mth function of this series, is 0. Note that gmy is 0 for all y belongs to R, and it is a constant function, and hence it is continuous on whole of R. Note that m minus n whole square plus y minus n whole square is not equal to 0 for all n belongs to n, for all n not equal to m, for all y belongs to R. So when n not equal to m, m minus n is not 0, its square is not 0, the whole is not 0. And this is true for all n belongs to n, for all y belongs to R, when n not equal to m. So that means this g and y, when n not equal to m, is also continuous, because the denominator is continuous, obviously the numerator is continuous, and hence g and y, n belongs to n, n not equal to m is continuous for all y belongs to R, therefore it is continuous on the whole of R. Thus, each term sigma n is equal to 1 to infinity g and y, n belongs to n, are continuous on R. Now, we will see what happens to this series, and let us talk about the uniform convergence of the sigma g and y. Now, mod of g and y is equal to mod of this, and 1 by 2 power into mod of this, and mod of this is less than or equal to 1, and that is less than or equal to 1 by 2 power n, that is equal to mn, and sigma mn is 1 by sigma 1 by 2 power n is convergent. By Weierstrass mn test, sigma n is equal to 1 to infinity g and y is uniformly convergent on R. By continuity theorem, why we can apply? So each term g and y is continuous, and the sigma n is equal to 1 to infinity g and y is uniformly continuous on R. By continuity theorem, it's some function h of y that is equal to g of m comma y is equal to sigma n is equal to 1 to infinity g and y is continuous on R when c is equal to m belongs to n. How m is chosen? M is chosen arbitrarily, and hy is equal to g of c comma y is continuous on R when c belongs to n, because m is arbitrary. And so combining the two cases, that is the first case when c does not belong to n, when c is a real number but not a natural number, and the case 2 when c is a natural number. Combining these two cases, the function h of y is equal to g of c comma y is continuous on R for all c, So this proves the option 1 is true. Thus, our answer is options 1 and 4 are true, and the options 2 and 3 are not true. Thus, we have come to the end of the discussion of the solution of this good problem, a wonderful problem, on series of functions of two variables and its uniform convergence. I hope that you have understood the solution of this series. I wish you all the best. Thank you.